Okay, what we're going to get into now is the equivalent of, when we're dealing with particles, we use Newton's second law to relate kinematics to the causes of the motion. With rigid bodies, we still have that translational stuff that happens with particles, but we also have the possibility of objects changing orientation, spinning in some way. And so what we're going to have as our, what was Newton's second law for particles is now going to be two equations. So for rigid bodies, we still have Newton's second law. And that says that if you add up all the forces on whatever body you're isolating, that's equal to the mass of the object times the acceleration. We're used to that idea, but now we have to be very clear about what point of the acceleration we have. You've seen in your rigid body kinematics problems that two different points on a body, on the same body, can have different accelerations. So what matters here is the acceleration of the body's center of mass. Okay? And just like with particles, if you're doing this in 2D, which is all we're going to do, this gives two equations. And now there's a new equation that we're going to use. I'm going to call it Rn2L. It's like the rotational version of Newton's second law. That's what the R is for, rotational Newton's second law. And this says if you add up all the moments about a body, all the moments on a body about some point A, about some axis, add them all up, that's equal to this capital I. It's called the mass moment of inertia about a point A, that same axis, times the angular acceleration. And if we're doing this in 2D, then all the rotations are happening about one axis. They're just happening in a plane. And so in 2D, this gives one more equation. And so all together, these give three total equations. Okay, so, and by the way, we'll see that there are restrictions on what this axis can be, what you can choose as your point A. I know that doesn't mean much to us so far, but A has to be either a fixed point, like a place where the object has a hinge or something that rotates, that's connected to the coordinate system. Usually the ground, connected to something fixed, something that can't move. Or, because not every body in 2D has a point that's fixed, it can also be the center of mass. Okay, well, before we can use these equations and figure out useful things with objects, we have to define a few things. So we have to define center of mass, the mass moment of inertia about A, and the third one is we have to define what these moments are, these things that produce the rotations about that axis A. These are the two that we're going to do in this lecture today, and then we'll talk about moments next time. Okay, well, the center of mass to us is not, it's not a very complicated discussion. In 2 dimensions, the center of mass is at an object's geometric center. Which is called the centroid. And the thing that's going to be important for us is that the centroid always has to lie on any axis of symmetry you can find for the body. Okay, so let's do a few examples, and you can see that for simple shapes, the kind of shapes that we're going to use, this is all we need. So an example is a rectangle. Let's also do a circle, and then let's think about a shape that's, I'll tell you how this is different, but imagine that's a bowling pin. Imagine I drew it better. Okay, so where can we find axes of symmetry for these shapes? For the rectangle, this is an axis of symmetry. One way you can think of an axis of symmetry is like, can you fold the shape along that line, and will there be any overhang of either side over the other sides? And you can see that with a rectangle, if you folded it along that red line, it would exactly match up. So that's an axis of symmetry. And you have another one like this. And so what that means is where those two, since the centroid and the center of mass have to lie on those axes of symmetry, the place where they intersect has to be the centroid and has to be the center of mass. Okay. What about with a circle? There's one. There's one. For a circle, unlike a rectangle, we can keep making these. You know, there are infinitely many of these. So where's the center of mass? Well, in this case, all of these axes of symmetry intersect at the same exact point, and that point where they intersect is the center of mass. And so you don't need any math to figure out where the center of mass is for things that have 2 axes of symmetry or more. Okay, so shapes like this, you can just eyeball it, you know that the center of mass is right in the center. What about something like this? Okay, well, it has an axis of symmetry like that, but it doesn't have a second one, which means in this case, we would have to calculate where the center of mass lies. And I'm not going to get into how to do that calculation. We're going to deal with simple shapes like thin rods, rectangles, squares, circles, and so we don't need to know this. Another one that could come in handy is an equilateral triangle. Well, that has an axis of symmetry here, here, and a third one for good measure. Whenever you have more than 2, they have to all intersect at the same point. And so that's where the center of mass is. Okay, so thinking back, relating this to Newton's second law, what we know is if you find this center of mass, and then you figure out what all the forces are that are acting on the body, whether it's spinning or whatever, the acceleration of that point, of that center of mass, times the object's mass has to equal the sum of all the forces, the net force. Okay, and next, let's define the mass moment of inertia. And I'm going to think of this as the mass moment of inertia about an axis A. Okay. Well, what was mass? The way I defined mass earlier, before we used Newton's second law, was an object's resistance to acceleration. Well, you can think of the mass moment of inertia as an object's resistance to rotation about that axis A. So you can imagine an object having a hinge at the point A. If we're thinking in 2D, that axis is just a point. It's going into and out of the page. And if you have a hinge at that point, the question is, how hard is that body to get rotating around that hinge? One example that I think people can usually sort of visualize is when people are doing gymnastics, like say they're doing flips in gymnastics. There are multiple ways you can position your body to do flips, and some are easier and some are harder. So why is that? Why does it vary? Well, let's think about two positions. So here's one way you can do a flip. Okay, so say that this person is flipping this way, and let's say that the center of mass of their body is here. Okay, so you can think of that as the hinge. And another way they can do flips is hold their body in this position. Okay, and their center of mass is here. Okay, well, they could do a flip this way, the laid out position, and they could do a flip in the tucked position, the other kind. And there's different, they get different levels of difficulty for doing these things. The laid out position is harder. And it's harder because it has a big value of the mass moment of inertia. And what it means to have a big mass moment of inertia is that the person's mass so the mass is spread out far from the axis, which in this case is the center of mass. So think of the hinge at the center of mass. There's a lot of mass spread far away. This is easier. The reason it's easier is because it's easier to get the body in this shape rotating. And so you don't have to get up as high to complete a full flip or two flips or whatever you're doing. This is a small value of the mass moment of inertia about the axis. And that's because the mass is close to the axis, which is the center of mass. Okay? So if you, even though it's the same mass, if you spread that mass as far as possible from the center of mass, it's hard to get the shape rotating. If you pull it all in tight to the center of mass, it's easy to get it rotating. That's the idea of mass moment of inertia. There's an integral definition for mass moment of inertia, but we don't have to worry about that. So we're going to use algebraic formulas for the mass moment of inertia that come from the integral formula. And so I'm just going to give you these formulas for the shapes that we're going to use. So the mass moment of inertia about the center of mass for three common shapes. The first one is a slender rod. Okay, the center of mass is right in the middle. And let's say that it has a length L and a mass M. Then the mass moment of inertia about the center of mass for this shape is 1/12 times the mass times the length squared. The second shape we're going to use a lot is a rectangle. The center of mass, like we talked about, is right where the two axes of symmetry intersect. Let's say that along one axis, the length is, we'll call that the width, W. And along the other axis, we'll call it L, length. Then the mass moment of inertia about the center of mass, a measure of how hard it is to get this shape rotating, is 1/12 times the mass times the quantity, width squared plus length squared. And the last shape that's going to be important for us is a disk. Center of mass is right in the middle. And the radius is R. Well, the mass moment of inertia of this disk around its center of mass is 1/2 m r squared. The units for mass moment of inertia are, well, you can figure it out from the formula. It's going to have units of mass times units of length squared. And so in SI units, that's kilograms meters squared. Okay, well, it turns out to be the case that it's depending on where the hinge is, the same shape is, different difficulty to get that shape rotating depending on where the hinge is. So with the slender rod, if the hinge is at the center, where I have it drawn here, and what that formula represents, it's relatively easy to get it rotating. If the hinge is at one of the ends, it's harder to get it rotating. And so, given that fact, having these formulas doesn't seem very helpful because these are just for the center of mass. And really, we would need infinitely many formulas to represent the mass moment of inertias for all the different places where that hinge could be. That seems like a problem, except there's a simple solution to this. So notice this only, these formulas only work for an axis at the center of mass. What if the axis of rotation is somewhere else? Well, it turns out that there's a simple solution to that too, and it's called the parallel axis theorem. And without this parallel axis theorem, this would be a really major problem that we would have. Or I guess what it would really mean is that you would have to use the integral definition every time. These integrals can be complicated, and we'd really like not to have to do that. Okay, so now the parallel axis theorem. For an axis A that's a distance d, lowercase d, from the center of mass, the mass moment of inertia about that axis that now is not at the center of mass is equal to the mass moment of inertia about the center of mass plus this correction factor that's equal to the object's mass times that distance d squared. So there's the parallel axis theorem, and what it says is we can use those formulas for the moment of inertia about the center of mass, apply this correction factor, and that'll let us calculate the mass moment of inertia for any axis we want. Okay? One other thing to pay attention to here, notice that md squared, since mass is always positive, d squared is always positive. The biggest, this always has to be positive, this term. And so the smallest value of the mass moment of inertia you can have is the object rotating about its center of mass. Any other location for the axis makes it harder to rotate, makes the mass moment of inertia bigger. Okay. Okay, so here's an example. It's a slender rod. And the center of mass is here. And let's say it has a length L. But let's say that we want to calculate the mass moment of inertia about A, So what's I sub A? And this would be something that you'd have to do if you're doing a calculation where there's a hinge, physically a hinge connecting this rod to the ground at that point. You need to calculate the moment of inertia about A, about that hinge. Okay. Well, what's the distance from the center of mass to A? The length of the whole thing is L, so that distance D is L over 2. Okay. And so the mass moment of inertia about A is equal to the mass moment of inertia about the center of mass, and we have a formula for that. That's 1/12 times the mass times the length squared, plus, using the parallel axis theorem, the mass times d squared Okay, so that's 1/12 mass L squared plus mass times L squared over 4. And now we can get a common denominator. ML squared over 4 is 3 ML squared over 12. And so all this comes out to be 3/12 plus 1/12, so 4/12 ML squared. And now you can reduce that and you get 1/3 ML squared. So what that tells us is that if you're ever rotating a slender rod around one of its endpoints, the mass moment of inertia is this, which means that it's 4 times more difficult to get an object, a slender rod, rotated around its end than it is around its center of mass. And we have this for some simple shapes, but it turns out that if you have a shape, let's say a complicated shape, made out of, a combination of simple shapes, so let's say that we have a shape like this. Okay, we definitely don't have a formula for that, but we could break this up into things we do have formulas for, rectangles. Okay, and let's call this rectangle shape 1, 2, 3, and 4. Okay, and let's say that we want to calculate the mass moment of inertia of this shape around this axis. Well, the mass moment of inertia of the whole thing about A is just the sum of the mass moment of inertias of those simple shapes. So mass moment of inertia of rectangle 1 about A, so you're going to have to use the parallel axis theorem for these, plus mass moment of inertia of 2 about A, plus mass moment of inertia of 3 about A, plus the mass moment of inertia of 4 about A. And you can do this with subtraction too, like if you have a shape that's, let's say we have a shape like this, where, so this is the solid part. You could calculate the moment of inertia of this by calculating the moment of inertia for the big rectangle and then subtracting the moment of inertia for the circle. Okay, so that's how to do calculations for mass moment of inertia. And then next time, remember, we're trying to get ready to use that rotational version in Newton's second law. So the next thing we have to define is the moment. And once we do that, we'll be able to use that rotational version in Newton's second law.